There we go. All right, we're going to talk about pumps and pressure. Why is that thing got to be that way up there like that? Pumps and that says pressure carbs. Pumps and pressure cards. I don't know. I didn't update the reading. You definitely want to look at the reading in Canvas. That is the most accurate. So pumps and pressure carbs. And that's what we're going to talk about. And the reason why we want to move off and start talking about pumps is because when we talk about pressure carburetors, fuel injection, we actually have to have fuel pumps to operate these things. And if you don't understand how the fuel pump is operating and what's going on with that, then it's not going to make much sense on how the pressure carburetor or fuel injection system is functioning. So I want to tell you that it's going to be critical that you have a concept of, I want to say, fluid dynamics, that you're not just memorizing how something goes through a pump, but that you actually take the time and think about what is really happening and why it's happening. Because if you don't, things are going to start falling apart for you conceptually as we move along. This is one of those things that's going to build, it's going to build. And I know we took a long time. That was like 4, 5 days. So that's the equivalent of 10 regular lab days just to get through section 1. And that's okay, because as we move on through this, there's going to be a lot of times where I can simply say, all right, we've just talked about this, and this works exactly like that. Next subject. There's even times where where I can say, wait, remember how we just discussed that? Well, this works exactly like that, but these two chambers are changed. So you really want to pay attention. And where things get really ugly, so I just want to warn you, is when you get to running your fuel pump on the fuel pump stand, and you're going to be messing with an orifice and flow. And I'm going to ask you to explain to me the relationships between orifices and flow. And if you can't do it, I cannot pass you, because you just can't move forward with that. So not to scare you, because everybody in this class should not be in that problem. Everybody in this class is quite smart. And you can do it, but I want to warn you to make sure that you're paying attention and thinking it through, or you're just going to be stuck going back, listening to these lectures over and over again, trying to figure out what it was I was talking about because you missed it the first time. So anyway, so all right. So remember, fluid dynamics, how things work, how an orifice works in relationship to flow. So when we think about flow and pressure, flows and pressures, everything. So with that said, there are basically two types of pumps. Two types of pumps. And in the categories. So category 1, we will say constant displacement. Constant displacement. And constant displacement pumps would include gear type pumps. Gear type. And you've already experienced this with the Lycoming. The oil pressure pump on the back is a gear type pump. It is constant displacement, which is to say that for every single rotation, it will put out a constant amount of fluid. And of course, the faster it moves, the more fluid it's going to put out. The slower it moves, the less it's going to put out, but it is based upon revolutions. So the gear type pump. And
is it positive displacement too, right?
Yes. Yes, we can constant, actually, I could write that, constant displacement, or, oops, I hit a button I shouldn't have. Constant displacement, we could also say, yes, positive displacement. And then we have rotary vane. Rotary vane. I'm not aware of any gear type pumps that move fuel at all. Gear type pumps, oil, hydraulic fluid, but not fuel. And I think the reason why that is because you're talking about, with gear type pumps, lower volumes and higher pressures. And rotary vane pumps are going to be, they can still do some higher pressures, but much higher in the volume world for their weight.
And in a gear type pump, wouldn't the low viscosity of fuel play a factor into not being able to pressurize?
That is a wonderful statement right there. Lack of lubrication, as I can say. I don't want gears running around that aren't lubricated. Yes, because what lubricates the gears of an oil pump? Where does it get its oil? All right. So all of them will displace a given amount, So I should put this up here, actually, that would make more sense. We'll displace a given amount of liquid for each revolution. All right. And then the other type is for lack of a better term, a non-constant displacement. Pump, or also called a variable. Let me add that, variable displacement or variable displacement. All right, variable displacement. Well, what kind of pumps do those? Well, the one that comes to mind right away is when we talk about fuel, especially centrifugal. Centrifugal pumps are used as boost pumps. Used as boost pumps to deliver fuel to the engine-driven pump. Engine-driven pump. The engine-driven pump can actually be it's either going to be, honestly, a rotary vane or a variable displacement pump, diaphragm type pump. Those are the two types you're going to see, which is, of course, a variable displacement pump. But the centrifugal, it works off centrifugal force. And I think you guys probably talked a lot about this with Phil, especially when you talk about turbines, because the compressor on a turbine is, in fact, a centrifugal. Well, you have centrifugal compressors, right? Somebody say yes.
Yes.
Okay. Well, you can only say yes if it's true, though. I don't need to say yes if it's not true. So let me see. So here we have, out of your book, a centrifugal pump with an electric motor in there, because it's not engine driven if it's all the way out in the tank, and they're usually buried in the tank. They're actually, in order to change them out, you would have to drain all the fluid out of the tank to get to them a lot of times. So this is one type, centrifugal. Centrifugal does a couple of things. One, like I said, it provides fuel under pressure to the engine-driven pump. Number two, by providing fuel pressure through the whole system, we have less of a chance of vapor lock because we've increased pressure. The nice thing about centrifugal is it will, in fact, separate the air from the fuel. So you get, this is the centrifugal pump down here going down. And so with the impeller, so we can get fuel comes in and the air can get spread out from centrifugal force, so we can get less air molecules running up through the fuel. Of course, they are not constant displacement. They act more like a propeller on the front of the airplane. So propeller on the airplane is certainly not a constant displacement pump. It is more of a centrifugal item. So, all right. Close that. So it uses a boost pump. They are used during engine starting. They provide redundancy, so they used as a substitute for the engine-driven pump. If the engine-driven pump fails. As I said, they are good for separating air from fuel. Good for separating air from fuel. And a little bit redundant, but are not constant displacement. They kind of act like in the same way a propeller is not constant displacement. All right, so those are our two types of pumps. And I'm not going to spend very much time, that's about all the time I'm going to spend talking about the centrifugal pump, because that's really an airframe item. It is not an engine item. I just need you to know that that thing is out there in the fuel tank and it's spinning away, and it does provide fuel under pressure up to the engine-driven pump, and in case the engine-driven pump isn't working, all the way to the fuel control unit. And I'm going to say fuel control unit, which means carburetor, pressure carburetor, fuel injection system. So that's out there, it's working, but that's an airframe item. Doesn't mean I don't care about it. So it just means it's an airframe item. It means I don't care about it.
Kevin?
All right. What's that?
Yeah, if they fail, then you just change the whole unit.
Yes, you do.
You don't repair it, right?
The centrifugal out there in the wing.
Uh-huh.
You could. I would never do it. I'd never repair any type of pump, electrical pump that deals with fuel. Any sort of arcing can be a very bad thing. Let's see. There is another type of fuel pump. Let me see. I think I got a picture. I don't have a picture. What the heck? It's like the book doesn't even talk about them, which is funny. Oh, here's a picture of it. This is another type of fuel pump. So it's not a centrifugal fuel pump. I don't think your book talks about them at all. I don't think there's any questions about them, but they're actually quite common in aircraft. And they're even common in cars. In fact, you can pick this up at probably any AutoZone, and it's going to be the identical looking, tasting, and smelling part. And these things work, they're electrical, and they work off pulsations. So there's magnets in there and a pulsating diaphragm that pulsates off electrical pressure. And so it just allows fuel to come in one way and pushes out the other. This right here is actually a screen in there. So you can undo this and get in there and clean out the screen. But these are very common in aviation. And so when I see them and I know that an aircraft has it, every annual, I'm going to pull this piece off and I'm going to go in there and I'm going to clean it out and make sure it's okay. But they are also, they're a little bit slower. Okay, so let's go back to, we're going to talk about the rotary vane pump. We're going to really talk about two different pumps in this class. One is the rotary vane and the other is going to be the diaphragm. So rotary vane pump. Rotary vane pump. Let's see here. So this is my rotary vane pump. And they haven't really changed what they look like in a very long time. So it is in fact engine driven. That's what this is down here. That slides into a gear in the interior of a gear shaft. And so it's driven right there. It is necked way down like this. This shaft is very small for a good reason. That's called a shear shaft. So should this pump seize up and fail, it is designed to shear this shaft right here rather than causing any damage or stress or strain to the engine. All of these red caps are plastic. They are for shipping only and should never be used on an actual installation. All right, so the inner workings. So what they have in there is, it's called a rotary vane because of these veins that have in there. This one obviously has 4 veins. And it works in a way that this little spacer pushes these out at certain times. So you can see it's concentric. It's not, this is offset. So you have a large space up here and a small space down here. And these veins in relation to this right here slide in and out. So you can see the arrow, it's going this way. So we have the fuel is going to come in here. And as this vein is rolling through, it's going to create a space in here that is going to be, it's open up through here. So this is a pretty big space, but over here, it's all locked off. So at this point, this is filled full of fuel. This right here is, this sucks in the fuel. This is full of fuel, and it is going to force under pressure, constant displacement, this amount of fuel down and out. So nothing real complicated about it. The thing about these that is a little complicated is sometimes these vanes are made out of a steel, and sometimes they're made out of carbon. And if they're made out of carbon, they're actually quite brittle. This is the exact same design as vacuum pumps. In fact, you could just relabel this vacuum pump and I wouldn't have known the difference because it's exactly what a vacuum pump looks like, tastes like, smells like. But in this case, this one happens to be for fuel because it says, maybe not, it says Rotaryvane, yeah, fuel pump, because it says fuel pump. That's how I know it's fuel pump, because it says so. All right, so let's talk about the inner workings of it, because it's not that simple. I mean, it's how it pumps, but you can't just make a fuel pump like this. It wouldn't work. I mean, it would work, but not for aircraft. You'd have all kinds of problems. Problem number one is its constant displacement. And so what are you going to do with the fuel that you don't want? So you got to make some sort of relief for it. Problem number two, what happens if this thing does shear and the shear shaft goes? And so here's the inlet, and we have our boost pumps. Like, well, okay, well, this shears off and it stops and freezes like this. Then I run my boost pump, but the boost pump is going to boost fuel and it's going to come to right here and stop. So I have no way to get that boost pump fuel around. So that wouldn't work as a backup. So this is the basic design, but this is what it looks like in reality, which at first glance, it's like, what the heck? But it's really nothing major. So we just talked about how the pump right here works. And so nothing's really changed. This is how the pump works, right? Fuel comes through here, gets into this little cavity. This is obviously going around this way because it would not work if it went that way. It can't go in the small spot. So fuel gets in here, comes around through here. It's squeezed and pressed out this way and off it goes. But we have to think about a couple of things. Number one, I said that the centrifugal pump is used for starting the aircraft. And the centrifugal pump is also used as a backup. So that means we must have some way around it in case things don't work. Well, the way that works is if this pump is not running, like the engine's not running, so I run the boost pump, pump's going to come, fuel's going to come this way, and it's going to come out, and I always got to think about how this goes here. It's not going to make it through anywhere here, so it's got to come up, and it's got to find its way down through here. And so that's what this spring is for here. It'd be easier to look at, I think, if it didn't have all these lines all over the place. I didn't put them there. Actually, I'll go this way. There's the backup. So what it's doing is it's coming this way and it pushes down on this little plate right here through these holes, in this example, these holes that were drilled around, finds its way through there and down. Now, one of the big questions is going to be that I'm going to ask you, well, how long and when is the bypass valve going to be open? And the simple answer is the bypass will be open as long as the boost pump pressure is more than this pump's pressure. So think that through. So if this pump is running and it's putting out 1 PSI, but the boost pump is running and it's putting out, say, 5 PSI, this does not have enough pressure to go this way and close that, because the boost pump is always going to have more pressure, so it's going to push this down. It's like a push-a-war, if you will. Is this one going to push and win the war to push this up, or is the boost pump going to win and push this down? And it says weak spring. They're not kidding. That spring is only just strong enough to keep this plate up and touching. That is it. It depends upon the fuel pump pressure, this pump, to keep that up in place once it's running and closed. So when does the bypass valve close? Whenever the boost pump pressure exceeds the engine-driven pump pressure. This is an engine-driven pump. So that is how it does. So if this thing were to seize and stop, well, the boost pump pressure is going to win. It's going to find its way through there, and it's going to go off to the fuel control unit and operate the engine. if I'm trying to start this aircraft up, this is engine driven, so clearly it's not running. So in order to get fuel to the fuel control device, I have to run the boost pump, and it's going to come around and go like that. In the carburetors that we talked about, I told you, and we talked about how the carburetors don't have enough airflow on the starter to start them. So you had to have a primer. Once we get into aircraft that are fuel injected, and even a lot of aircraft that are pressure carburetor, they don't have any sort of primer system. Fuel injection, engines with fuel injection rarely have a primer system. The only one I'm aware of is the Skymasters that we actually have outside have a manual primer and a fuel injection system. I love them because it makes life so much easier. But otherwise, you actually prime the engine off of the fuel injection system. And so it takes a pretty deep understanding of how the fuel injection system works to not destroy the engine and actually get it off and running. So, okay, so that's how the bypass works. I'm gonna go back one in theory. There we go. Okay, so we have the bypass. Now, in addition to having the bypass, so we get this pump up and running, and it's doing its job. We can actually shut down. We don't even need the boost pump anymore. Most aircraft POH, the Pilot Operating Handbook, will tell you that you should run the boost pump during takeoff and landing. Now, the exception to this is most Continental engines don't like that. You're going to learn why much later on. That really messes with them. And they only really work well off the engine-driven pump. It's part of their design. But we get this thing off and running, and like any good pump, it really needs to put out more than the fuel control unit uses. It would be very difficult to design something that only created just the exact amount that it's needed, not a bit more. And then of course, once it starts wearing because it gets older, then it's going to be insufficient. So we have to have some sort of pressure relief valve. Well, that's what this one's doing. So here we've got the bypass valve plate is closed. So that should tell you one thing, and that is that the pressure of this pump is now higher than the boost pump pressure. All right, maybe the boost pressure's off. Well, that still means this is higher than the boost pressure. So, okay, so this thing's going and it's pumping away, and it's going out to the pressure carb or fuel injection unit, but that item only needs, a couple of gallons per hour, and this thing's, say it only needs 5 gallons per hour, and this thing's putting out 10 gallons per hour. So the fuel's got to go somewhere. So it's just going to find its way up, and now it's going to press this plate and this whole apparatus here up against this spring, around back to the inlet side of the pump. So if I actually had a barrel of fuel or something, and I decided I'm just going to block this off, I'm going to see what happens, and I hook this up to some sort of electric motor, that way I could watch what happens. What's going to happen? Actually, you guys are going to do that. You're going to hook it up to a tank with an electric motor in class. It's just going to come in here and it's just going to recirculate all day forever until it just gets tired and wears out. So, and the fuel gets too hot. It just goes and goes and goes. Not to make this too hard, but let's talk about it. So what it has up here then is a pressure adjustment. So if I take this and I put a pressure gauge on it, there's my pressure gauge, and I set it for, say, I want 25 PSI. All right. So now we got to start thinking about pressure. So this sets it for 25 PSI here at the outlet. And so if I want more pressure, I'm going to screw this down. Actually, there's usually a cap, and this is a cap, and the cap comes off. And then there's a screw down here for a screwdriver, and then you screw it down. So if I make this spring tighter or press it down, more pressure against this, then my pressure here is going to go up. If I loosen this, then my pressure is going to go down. Now, something to keep in mind is that you know how springs work. If it takes 25 PSI to make it go, compress it 1/8 of an inch, it takes 27 to make it go a little bit more, and it takes a little bit more pressure. So springs take more pressure to compress them all the way down, right? And so the pump is a little stupid in that respect, and that if I were to, let me see, we'll make a little hole here. So, oops, that was a big hole. And now I'm just going all over the place because I hit the wrong button. There we go. So if I want a pen, thank you. If I were to close this up most of the way, and so now I've got some sort of orifice right there, and I'm pumping out X number of gallons per hour, and I've set this for 25 PSI. If I increase the speed of the pump a lot, just to make it obvious, this isn't really going to stay at 25. It's going to creep up a little bit. It might go to 27. Why? Or 28. I don't know. It's going to go up because if I speed up the pump dramatically, only so much fuel can get out of this little orifice, which means more fuel has to be bypassed. And if more fuel has to be bypassed, then this has to open up further to let all that more fuel. And if this has to open up further, that means that the spring is going to get compressed a little bit more, and it takes a little more pressure to move it up. So just by the nature of the beast, you're going to see a slight increase in pressure as it goes. So if when you're working on these and you do see a slight increase of pressure because you doubled the speed of the pump, that's to be expected. All right. We'll talk more about that as we go. Let me think here. I know, hard to do. Let me see, we talked about that. We talked about that. And we will get around to that in a little bit.
Hey, Kevin, kind of a question for you. When you said it recycles through the pump on back there, if you were to hook up a tank to it and then have an electric motor, would it recycle back out the inlet, or would it just cycle through the pump? Would it
through the pump.
Okay, no, it wouldn't push it back.
Well, let me bring up the slide. It's exactly how it's drawn. They drew it 100% accurate. If it can't get out this way, or it's not using it, it comes up through here, back around to the inlet side of the pump.
Okay.
Right through this little mechanism. And that is all contained right here. So all of that spring stuff is, you can't see it in this picture. It's all right up in here. At least I think this one has it. I can't, it probably does. I'm not trying to look around it. I can't see it. All right, we'll write some notes. There's really not much more. There's one more thing to these pumps, but otherwise, that's the bulk of it right there. So, all right, where am I here? Rotaryvane pump. There we go. Rotaryvane. It is a constant displacement pump. It is a constant displacement pump. All right. And I'm going to repeat myself a little bit, but it's worth, I think, noting. Of course, you don't have to write it if you don't want to. We'll deliver a constant volume of fuel per revolution. That's the name, constant displacement. A pump does not pump pressure. That is cannot understate that. Pumps do not pump pressure. Pumps volume. It pumps volume. And well, I'll put this point and then I'll come back around because this ties it in together. A restriction in the outlet. A restriction in the outlet causes the pressure to build up. Causes the pressure to build up. Here, if If the restriction is removed, the pressure will go down. If the restriction is removed, the pressure will go down. Will go down. Now
Dog
we
sounds
could.
mad.
I know. It's apparently, yeah. Apparently it's dinner time and they want their food. Now, if I were a really good drawer, and I'm not, I will make an attempt to explain something.
That's a big if.
Yeah. All right. So at your house, you have a water faucet. That's what I'm trying to draw. So water faucet. There we go. There's our water faucet. With little, there we go. You have a water faucet, and attached to your water faucet, you may have a hose. There's Zeus. You may have a hose. Okay, so when you, and if I were to take, because, you know, we're aircraft mechanics and I just don't want any hose. I want a hose with a couple of pressure gauges to it. I don't know, what is standard house pressure? We'll just say it's 30 PSI. So I have 30 PSI. So with this closed, my faucet closed, I can look at that and say, well, I have 30 PSI. All right. And that's the pump pressure from the municipal utilities, and they're trying to give me 30 PSI. So with this handle closed, I have 30 PSI. And when I open this, they're going to do their best to try and maintain 30 PSI, but I no longer have quite the restriction. So when I open this, this is going to go down. All right. But then I look at my hose. Well, let me back up. When this was closed, what was my pressure in the hose here?
0.
Okay, 0. I got another one here. I got 0, and I've got nothing. So I open it up, and the pressure is going to go down a little bit. Let's say maybe it goes down to 28. Why? Because I've lost the restriction that was here, but I still have some restriction. It's not that big of a thing, so it goes down some. I don't know, depending on where it, maybe even less. But what is my pressure going to be in my hose?
Less than 30 as well.
It's a whole lot less. I don't have it. I have it wide open over here. I'm going to make up numbers. So maybe it's 5 PSI. You know, it's because there's a little bit of restriction at the end of the hose. Not very much at all. So we'll put a little bit of restriction there. And so I have a little bit of pressure is going to build up. But if I were to look at gallons per minute, so we'll do that. So now I've got another gauge, which is gallons per minute. And the only real way to measure gallons per minute is I would have to have something that would come down with a little wheel on it and a little spinny thing, and it would spin at a certain rate about the amount of fuel or water that would flow through it. And it would tell me my gallons per minute. So maybe I'm doing, let me see, think about how long it would take to fill up 10 gallons per minute, because it'd probably take me 1 minute to fill up 2 5-gallon buckets, right? So that's 10 gallons per minute. So there we go. So got my hose running. I don't have much pressure at all because I have almost no restriction whatsoever. And I'm getting 10 gallons per minute. So every minute I can fill up 2 5-gallon buckets. But then I decide, you know what? I want one of those like nozzles that are really kind of, you know, spray really far. And so I get one like that. So it sprays really far. And so that's a restriction. So now it's gone far, and I can spray my kids with the hose, and I like that. So what is going to happen, first of all, to my pressure?
Right.
All right. So the pressure now is going to go way up because I put a restriction. Now it depends on how big that restriction is. Let's say I made this go all the way down where I only had an 1/8 inch opening, and you guys know what an 1/8 inch is. That's a number 30 drill bit. So if I did an 1/8 inch opening, I'm probably going to see, if this is 30 coming in, I'm probably going to see 29.5 PSI, right?
Yeah.
It's going to be a lot of pressure. And what is my gallons per minute going to do?
Go way down.
It's going to go way down. You can't get 10 gallons per minute out of that. Let's think about how long it would take fill a 5-gallon bucket with an 1/8 inch tube. It would probably take me 5 minutes to fill up a bucket like that. So we'll just say maybe 1 gallon per minute. Okay, so you have to kind of look at this relationship of what's going on. So when you create the restriction, pressure goes way up and the gallons per minute is going to go way down out from the outlet. So keep that in mind. But of course, you also have to keep in mind, we're talking about a constant displacement pump. The amount of fluid going around the pump itself remains constant per RPM, but how much is leaving is something completely different. So, all right. So my point would be a pump pumps volume, not pressure. So if I go back and look at this pump right here, and I'm doing 100 RPM, but the pump outlet looks like that. I have no restriction. And I'm going at 100 gallons per, I'm 100 RPM. What do you think my outlet pressure would be on this pump right now?
Whatever your head pressure is, maybe a little more.
Probably almost nothing. I would have probably no, because the pump doesn't pump pressure, it pumps volume. And do I have a restriction?
Nope.
Nope. So I could, I'm gonna go back this way. Okay. I don't really want that one. I want, because that's bypassing. So you say, well, no, that's pressure relief. That's fine. So pressure relief. So if I look at it and I put a, well, that didn't work now. There we go. Need a pen.
Oh, it's 620, by the way.
Oh, 620. Oh, okay, well, appreciate that. Well, this is probably a good place to take a break then and come back and talk a little bit later.
Okay.
Woohoo!
Okay.
Dinner time.